For this mini lecture, we are going to talk about surface gravity of a planet, of a moon, of any celestial body. Surface gravity is the acceleration a mass undergoes at the surface of a celestial object. So when I'm talking to my physics students especially, I'll talk about the acceleration due to gravity. That value for our Earth is 9.8 meters per second squared. That means that anytime I drop an object, that object is going to be accelerating to the surface of the Earth at a rate of 9.8 meters per second squared. The thing that gives our bodies weight when we step on the scale, that's our mass times our gravity, or the mass times the surface gravity of our planet Earth is the thing that gives us weight. It influences the shape of celestial objects, and it influences whether or not a celestial object has an atmosphere. So a celestial object needs to have a fairly large surface gravity in order to be able to hold on to an atmosphere. For example, here we have a picture of the moon. This is a picture taken on the moon during one of the Apollo missions. The moon has a pretty small surface gravity compared to the Earth. Because of that small surface gravity, the moon is not able to hold on to an atmosphere. And here we see the flag that was stuck in the lunar surface. Because of that low surface gravity and the fact that, moon doesn't really have much of an atmosphere, they had to put a little post in top here of this American flag to keep it upright so that it would look like the picture that you're seeing here. And you see these little crinkles in the fabric of the flag. That's not wind blowing on the moon. There is no wind on the moon. The moon has, again, no atmosphere. So because of, again, that low surface gravity on the moon, pretty much with this fabric, whenever you sort of move it around and put it in place, it kind of just stays there. There's nothing that's going to try to pull it, not as much of an acceleration due to gravity that's trying to pull that material down to the surface of the moon. The surface gravity of an object is determined from Newton's second law, our F equals ma, and the universal law of gravitation. We have to take our Newton's second law, that has to be equal to the gravitational force between the smaller mass, u, and the larger mass, which is the planet. So we've got, let's say I'm trying to figure out the acceleration due to gravity on our planet, on Earth. I've got my mass times the acceleration that I'm feeling as I'm on the planet, and that has to equal the gravitational force between Earth and me. Okay, and that's what this equation is here. The gravitational force between big M would be the mass of the Earth, little m would be my mass. And in this case, r is the distance between me standing on the surface of the Earth and the Earth's center. So we see that on both sides of this equation, we've got the little m, that's my mass, and I can cancel that out. And then you're left with just a would be equal to g times big M over r squared. That a is the surface gravity of the planet, which sometimes we also refer to as lowercase g, little g. So the surface gravity is denoted by big G, which is our gravitational constant, which I haven't told you what that is. I'm not going to ask you to do any calculations with it. Anyway, so our surface gravity on a planet is equal to the gravitational constant times the mass of that big body, the mass of that large body, whether it's the mass of the moon or the mass of the Earth, divided by this r, in this case, is the radius of that object squared. Okay, so m is the mass and radius of your celestial, m is the mass of your celestial object. R is the radius of the celestial object in this case. Okay, so if we calculate this using the mass of the Earth and the radius of the Earth, this surface gravity, this acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. If we calculate this for the moon, we find that the gravitational acceleration on the Earth is 5.6 times that of the moon. And the gravitational acceleration on Jupiter is 3 times that of the Earth, okay? And that's because, well, Jupiter is much more massive than our Earth. It also has a bigger radius, but it's incredibly much more massive. And so that's why the surface gravity on Jupiter is larger than it is on the Earth. And the surface gravity on the moon, well, the moon is a smaller mass and a much smaller radius. And so the surface gravity on the moon as compared to the Earth is going to be much, much smaller. So our Earth's surface gravity is 5.6 times that of the moon. That's why the astronauts had to be careful and learn how to walk on the surface of the moon, because if you jump too hard, you might end up floating off into space. That acceleration due to gravity, the surface gravity of a planet, is what's pulling you and holding you to stay and walk on the surface of that planet. And we're all used to what that is like here on the Earth. So this surface gravity depends on 2 things: the mass of the large body and its radius. So your weight is the force that Earth's gravity is exerting on you. Okay, so your weight is your mass times the acceleration due to gravity, or the surface gravity of that planet. So to calculate your weight in newtons, you would take your mass in kilograms and multiply it by 9.8 meters per second squared. You could also do it in imperial units, and your weight in imperial units is what you read whenever you step on the scale, and that would be in pounds. So in standard physics notation, we use units of force as newtons, but if we're thinking about our weight, you could also use units of force as pounds. Your weight will change if you are on a different celestial body. So this G, this acceleration due to gravity, or the surface gravity on the surface of the planet, changes when you change the mass and radius of the planet. So if I go to the moon, my weight is going to be, take my weight on Earth, divide it by 5.6, that's how much I would weigh on the surface of the moon. If I go to Jupiter and try to weigh myself at Jupiter, my weight is going to be 3 times greater than it is here on Earth, because the surface gravity of Jupiter is 3 times greater than it is of Earth. Our mass is something that never changes. That's how much stuff we're made up of, but the acceleration due to gravity, or the surface gravity of a planet, is always dependent on that planet's mass and size. Okay, so let's talk about why astronauts then feel weightless, or why we always see astronauts and people in space floating around. Well, if we're thinking about just at the distance above our Earth, where the International Space Station is, or where the space shuttle used to orbit, that distance is really actually close to us. It's only 220 miles above our Earth's surface. That's not really that far when we think about how large our universe is. Astronauts that were on the space shuttle, astronauts that are in the International Space Station, are only 220 miles above our surface of the planet. That's really close. And that's 350 kilometers above the Earth. Okay, but at that height above the Earth's surface, the gravity from Earth is still 90% as strong as it is on the Earth's surface. So you have to go pretty far out away from our Earth in order to feel a large reduction of this surface gravity of the planet. In order for you to truly feel no gravitational pull from the Earth, you have to be really, really, really far away. Okay, so why then are astronauts weightless? Well, here's why. Astronauts on the space station have the same motion as the space station. That's what makes them feel weightless. The astronauts are literally falling around the Earth. So we talked about how if you give an object enough of a velocity, you can get it in orbit around a planet. Okay, and so what happens is that the International Space Station is in orbit around our planet. Okay, and the people inside the International Space Station are then also in orbit around our planet. So they, at the same time, are constantly orbiting our planet, kind of falling around the surface of our planet. And so that's why they feel weightless. It's the force of the ground that we're standing on or sitting on back up on you that causes you to feel the weight on you. So if you're in a spaceship that is falling at the same rate as you are around a planet, then there's not going to be anything to push back up on you. You would be almost truly weightless if you were floating around in empty space really, really, really far from any astronomical body. So if you got yourself somehow outside of our solar system in the interstellar medium between other solar systems, then if there's no astronomical body nearby, nothing to pull on you with the gravitational force that's nearby, then you might truly, truly feel weightless. So how do we, in the first place, overcome this gravitational force, this gravitational pull that the Earth has on us in order to send a spacecraft out into space? To overcome a celestial object's gravitational force and escape into space, a mass must obtain a critical speed that we call the escape velocity. The escape velocity determines if a spacecraft can move from one planet to another, if we can get it off this planet and get it somewhere else. It influences whether or not a celestial object has an atmosphere, and it also relates to the nature of black holes. We will talk about that later in the semester. Okay, so the escape velocity, the equation for it, is determined from Newton's law of motion and our universal law of gravitation. I'm not going to derive it here for you. My picture is probably covering up the equation for escape velocity. But the equation for escape velocity is the escape velocity from a celestial body is equal to the square root of 2 times the gravitational constant times the mass of that celestial body divided by its radius. So you've got, it's equal to the square root of 2 capital G mass divided by radius. If we do the calculations for Earth, the escape velocity for Earth is 11 kilometers per second. If an object has too low of an escape velocity, if its velocity is lower than the escape velocity of a planet, it's not going to be able to leave the planet and it's going to fall back down to the surface. If the velocity of the object that you're launching exceeds the escape velocity of the planet, then you can launch it off and away to other parts of the solar system. The moon, since it has such a small mass, has a low escape velocity of about 2.4 kilometers per second, much smaller than the 11 kilometers per second that we have for the Earth. So because of this low escape velocity, gas molecules that are on the moon are able to escape into space. That means that the moon really has almost no atmosphere. Any gas molecule that's going to be there near the surface of the moon can achieve a velocity on their own to exceed that of the escape velocity for the planet. And so that's why the moon doesn't really have an atmosphere to speak of. If the moon had a larger mass, it would be able to hold on to more material for its atmosphere. Okay, so then large mass objects like our Earth, having a much larger escape velocity, it's harder for gas molecules to exceed the escape velocity of our planet. And so then we are able to actually form an atmosphere. So if you're thinking about the things required for habitability of a planet or a moon, you need to probably have a fair amount of gravity in order to even hold on to an atmosphere, if you think an atmosphere is important for the development of life on the planet.